Okay, hello everybody and welcome to Astronomy on Tap in February 2021. It's good to have you back. We hope that you will enjoy the exciting program we have tonight, all about February being the month of Valentine's, all about stellar couples and how they interact with each other. So Astronomy on Tap has been going for a couple of years now, since 2013. It started in New York City in the States. And has spread all over the US and then also across the world. And we here in Leiden were the first Astronomy on Tap in Europe, and we've been running since 2017. You've probably already found us on social media, but we're on YouTube, obviously, but we're also on Facebook, Twitter, and Instagram. And you can always email us. We have a newsletter that goes out. It's the only reason we use the email. But if you're on social media, do give us a shout. Interact with us on Instagram and Twitter. And if you're watching live now in the YouTube, give us a shout in the channel, in the chat on the side. Tell us where you're from, where you're watching. And just to note, this is really just the talks are presented through YouTube, but you have the opportunity to ask questions to the speakers. So if you have a question at any point, you can just write it down in the chat, and we will ask the speakers the questions after their talk. So it's a good idea to write the question down immediately you think of it, because we have a little bit of delay between the speaker speaking and the questions. So it's nice to get the ball rolling if you have questions ready to ask them. But first up, we have very briefly some astronomy news. Last Friday, or was it Saturday night? I can't remember now. It was really exciting in the world of space. Another rover landed on Mars. I should just note that there have been several missions to Mars, and not all of them are successful, but it's really nice to see a successful landing on Mars. And this is a really cool one. This rover Perseverance landed successfully, and it will actually be launching a little helicopter to fly around. So this was the first image that made it back. It's amazing to see these images come through so quickly after the rover has landed. And this image comes from the hazard camera that checks out where the rover is going to drive. Really amazing pictures. And a slightly different amazing picture also released last week. This is some work that I work on myself, so it's close to my heart. But we've released another really cool image of a large portion of the sky. It's still only 2% of the sky, but it's several times the size of the moon. And it looks like a picture of stars in the sky, but in fact, it's actually images of black holes all over the universe. And this is light that's detected with a radio telescope, and the wavelength of this light is 6 meters. So this is really cool, new image released last week. So on to tonight. Tonight we have, as I said, an exciting program about stellar couples. First up, we have Jakub Klencki. Then we will have a short break. Then we have our quiz. We'll share the Google form link for you to participate in our quiz. We hope you have fun doing this. Then we'll have a short break, and then we'll have our second speaker, Nadia Blagorodnova, and then wrap up with questions from that talk, followed by the presentation of the quiz answers, solutions to some of the questions, and then we finish up the night. So first up, we have Jakub Klencki. He is a graduate student at Radboud University. He's interested mostly in the lives of the most massive and luminous stars and how they die in supernovae explosions. And all the kinds of after effects you get from these massive stars like neutron stars and black holes. He works with computational simulations, how these stars evolve when they live so close to each other. And because they live so close to each other, they interact strongly with each other. And he's going to be talking a lot about how gravitational wave astronomy, which is actually really, really new, but is making a huge impact in the world of astronomy, how it's opened a new window on the sky and understanding these massive stars and their remnants. A fun fact, and this is the picture you see here, Jakub really is not, he says he's not a great cook, but he really does enjoy it and he enjoys giving it his best. So here's a picture of him in a cooking class in Vietnam. So over to you, Jakub.
Okay, great. So hello, everybody. Indeed, today I will talk about gravitational wave astronomy, and in particular about the sources of gravitational waves that we can see with the current detectors. So right now, we're almost precisely 5 years after some of the biggest headlines in the science-related journalism. We could read 5 years ago about the gravitational wave detection heralding new era. A new era of astronomy begins, a discovery that won't just open a new window on the cosmos, it'll smash the door wide open. We talked about reshaping of physics, really big breakthrough. And in the same time, there have been hundreds, if not probably thousands by now, scientific articles being published on the topic of gravitational wave sources. And of course, last but not least, the Nobel Prize in Physics to boot for gravitational waves in 2017. So what's the fuss all about? What are we seeing? Well, black holes, basically. Now, there are probably many questions about black holes that you might have that I will not answer today. But I will say that a black hole is a region in space-time from which nothing, not even light, can escape from. I will be talking about stellar black holes, so not these supermassive black holes that Wendy just mentioned, but the black holes that are just a bit more massive than the sun, between 1 and 100 times more massive than the sun. And they tend to be very dense. So when you look at the sun, it has a radius of almost 1 million kilometers. But if you were to compress all that mass in the sun to form a black hole, then this object would be very small, with the event of horizon having the radius of about 3 kilometers. So really small, dense, strong gravity. But we're not just seeing black holes with gravitational wave detectors. We are seeing binaries, pairs of black holes. And when two black holes are orbiting each other, like the Earth going around the sun, they are perturbing the space-time in such a way that they emit gravitational waves. And those waves travel throughout the universe a little bit like waves traveling on a lake. And so these waves, we can observe them, but they also carry energy. So as a result of that, with time, the separation between the two black holes is decreasing. So they're getting closer and closer to one another, and as you can see in this simulation, eventually those two black holes will collide with each other, or merge, as we say. And that merger is what creates the most energetic emission of gravitational waves. And this merger, this very last episode, is what we can detect. So we can see binaries of black holes, close binaries of black holes, but we can also see binary neutron stars. And a historical note is that the binary pulsar was actually the first indirect observation of gravitational waves we had. The Hulse-Taylor binary pulsar, discovered in 1974. And we were fortunate enough to be able to observe it for a long time and to really track down the evolution of the orbit in this system. So here you can see in this diagram, as with time, over a few decades, we were able to observe how the orbit is shrinking in that binary as a result of gravitational wave emission. So this line here is a prediction from general relativity, and that prediction turned out to be spot on, matching the observations. And this is why there was a Nobel Prize in Physics awarded for that system. So essentially, already 2 Nobel Prizes awarded for gravitational waves. And in fact, 4 years ago, almost now, we observed a merger of binary neutron star system, also in gravitational waves, as well as in electromagnetic counterpart. That was one of the biggest events we've seen in astrophysics, in modern astrophysics recently. All right, so we can, with gravitational wave detectors, we can see binary neutron stars, binary black holes. But now, to learn about the universe from this, we need to ask ourselves the question, okay, where do these binaries come from? What is their origin? Which galaxies, which stars? And in fact, neutron stars and black holes most likely are remnants of the evolution of massive stars. So if we look at the simple diagram like this, low mass stars, low and intermediate mass stars, similar to Sun, roughly evolved through the stage that the Sun is now in, burning hydrogen. They later become giants and they finish their evolution as white dwarfs. But massive stars, more massive than 8 solar masses, more or less, well, initially they become similar, they evolve similarly, and they also become big giants. But when they finish their lives, they can explode in supernovae explosions that we see. And in the end, they become neutron stars, or if they're massive enough, they can collapse to form stellar black holes, those stellar black holes that we see in gravitational waves. So this is pretty great. With gravitational wave detectors, we can see the afterlives, the remnants of massive stars. And massive stars are very important in the universe in various aspects. So to gain a window into massive star evolution is pretty great already. But we talked about binaries, right? We don't only see black holes, we see binaries of black holes or binaries of neutron stars. So maybe this means that to form a black hole binary, well, maybe we need to start with a binary of two massive stars, right? This is not such a crazy idea, and Nadia will talk more about it later, that binaries are actually very common in the universe, and especially massive stars, they don't tend to live alone. They live in binaries or even triples. So we have a lot of those binaries, pairs of massive stars orbiting each other. But there is one problem here. There is a problem of separation. So in this final binary of two black holes that is going to merge due to gravitational wave emission, those two black holes need to be very close to one another for this emission of gravitational waves to be efficient to drive the system into merger. If they are too far away from each other, then the system is never going to merge within the age of the universe. So typically two black holes need to be closer than, say, 1/4 of the astronomical unit or a few tenths of a solar radii. But now the problem is that these massive stars that we think are progenitors of black holes and neutron stars, they get much bigger during their evolution, especially when they become giants. Their sizes could be of thousands of solar radii. So we cannot just put two massive stars very close to one another and let them evolve and hope to get this close binary, because crazy things would happen, potentially anyway. So this is a problem, and there are a few ways to go around that, and I will describe one of them. One idea is to actually start from a wide binary of two massive stars. So this is an initially orbit of 10 astronomical units, for instance. And I'll skip a little bit ahead up to the point when the first star, the more massive star initially, already collapses into a black hole. So we have a system of a black hole and a massive star. This second star is still burning hydrogen in the core, but the binary is still wide. So it's way too wide than we want it to be. Okay, but what happens then is that when the hydrogen fuel runs out in the center, this star will start to expand to become a giant, or even this red supergiant as I was talking before. And it is good to keep in this perspective how the structure of this star looks like, of a giant like this. So most of the mass is actually in the core or very close to the helium core. And all this envelope that is taking most of the volume is actually not very dense at all. It's pretty diluted. It's a little bit like just a cloud of gas with a star that essentially only in the very center, this hot helium core, okay? But this, nonetheless, this giant is getting very big. It is in a binary. And so at some point, it will start to transfer mass onto a black hole. Or actually, the black hole will start to gravitationally strip gas from the surface of this giant. And we know about such systems. We know about X-ray binaries in which a compact object, a neutron star or a black hole, is stripping gas from its stellar companion. And those are very exotic and very exciting systems on their own. But in this case, we want to keep going. We want to have this star that keeps expanding with respect to its orbit, gets bigger and bigger and bigger. And at some point, this black hole companion essentially is inside that envelope, all right? But I mean, this is still a binary system. So this black hole needs to keep moving on the orbit around this helium core. But because it's moving now inside this cloud of gas, there is a drag force which is slowing it down. So what's essentially happening is this black hole will start to spiral inside the envelope of the giant, and essentially will be getting closer and closer to the helium core. So the orbit between those two will be decreasing. And I will now show us a hydrodynamic simulation of this process, which was done for a slightly different star. That's a red giant, but the principle is very similar. And you can see this is the center of the giant, the core, and the spiraling in object is here, marked by this cross. Okay, and if I let this go, you can see that a white dwarf in this case is spiraling inside the envelope of the red giant, and it's getting closer and closer. The orbital period is shrinking, it's getting smaller, which is also the sign that the separation has decreased. And we get a closed binary. But what you can also see is that all this mass, all this envelope is actually getting ejected out of the system. And this ejection of mass is something that Nadia will talk a lot about in the next talk today. But what's great about this idea, well, is that you start from a binary that initially is wide. It has its giant and a companion, but because of all this spiraling in, and because of the ejection of this envelope during that spiral, what we get after is actually a closed binary of this black hole and the helium core and envelope being ejected. And once this helium core continues to evolve, finally collapses to form the second black hole, then we get a binary black hole system that is very small. And that's what we want. This system can merge due to gravitational wave emission. So that's what we wanted. So that's one idea, how to form these sources from binaries of massive stars. But I want to briefly describe an alternative. So not starting from a massive binary, but something else. And this alternative has to do with very crowded places in the universe. So our solar neighborhood, it turns out to be actually pretty empty. There's not many stars nearby sun itself. And if you look at this diagram here, on the y-axis, this is density on the logarithmic scale, and the solar neighborhood is somewhere here. But there are places in the universe which are much denser, clusters like this, where the density of stars is 10 to the 6 million times bigger than in our neighborhood. And in fact, we can observe these even with a binocular or small telescope from the Earth as global clusters in our galaxy, for instance. And to give an idea of how dense that really is, here's a diagram showing, here is the sun, let's say, and this is Alpha Centauri, which is the closest next star to us besides the sun. So normally in solar neighborhood, all this space is empty. There is no stars here. But if the density was as high as is in the center of a globular cluster, this is how many stars would be in that space. And this is an artistic image of how the night sky would look like with all these stars being nearby us. So that's pretty crazy. And because of this very high density, what's happening inside such clusters is that dynamical interactions between different stars are actually very common. And as a result of that, you don't need to start with a binary for two stars to at some point meet each other and create a binary. You can have triple stars interacting with each other. And in fact, the simulation on the right here is showing an interaction of a binary with a third star that is coming nearby. And as a result of all this mess that's happening, some of these interactions may lead to mergers, as you can see here, to mergers of stars, but also mergers of black holes, if those are black holes interacting here during this encounter. So basically another way to form these gravitational wave sources is to look into very dense environments in the universe when such dynamical encounters are common. So I've described now two ideas of how to form these gravitational wave sources that we've seen. There are many more ideas. You can divide them in the type of binary evolution that I showed one example of, into various dynamical channels, into mixed formation channels. There's also idea of primordial black holes that have been left after the Big Bang. So there's many ideas of how to form those. And actually one of the biggest challenges now in the field for us is to understand how to distinguish between channels. And for instance, we see one event detected in gravitational waves. Can we say which formation channel is responsible for that event. And we need to be able to address this question somehow to really use gravitational wave observations and detections to learn about the universe. And I want to finish on this slide to take a little bit of a different perspective. So I was talking all about these formation channels of gravitational wave sources, starting from massive stars and getting this binary of black holes, for instance. And this could be a very quick process that is only taking of the order of 10 million years, millions of years. And that's not very much compared to the age of the universe. That's actually very little. But this next stage, which is the inspiral of two black holes, for instance, until the merger, this can be very long, can be short as well, but it can be as long as the age of universe. So basically, it's possible that this, well, and the merger is just this final event. What we see here with gravitational wave detectors is just a few seconds or even a second of the final spiral. So really what's happening is there is this very long evolution. We see the very last bit, and it's a bit like hearing the final chord of a very long symphony, which I think is quite exciting. And what's also special about this is that the source that we detect, this could be coming from stars which had formed in early universe in very distant galaxies that we cannot observe otherwise, and that have traveled all throughout the cosmic history to merge finally and for us to see them. And this is what another thing that makes gravitational wave astronomy, I think, so unique. And I'll stop here and thank you very much for listening.
Great, thanks so much, Jacob. That was a fascinating talk. We do already have a question from YouTube. I just need to pull it up. So John Murray from New York. Hi, John. He has a question about which has the greater slowing effect on a black hole inside a red giant, the drag force of the gas or accumulation of mass within the black hole? So the black hole would be getting more massive and reducing its velocity.
That's a nice idea, actually. The second effect, especially. So the dominant effect, I believe, is the drag force. And actually, the way that this drag force works is that as the black hole is moving throughout the cloud of gas that is the envelope of a giant, behind the black hole, there will be an accumulation of matter. Because you have this black hole that is pulling all the mass from all of its surrounding, but it is also moving. So as a result of this pull, there will be an accumulation of gas behind that black hole. And that overdensity of gas behind the black hole will just drag it back through the gravity, essentially. And that's what is slowing it down. It's a form of dynamical drag that is slowing the black hole down. And I believe that is the dominant effect. But in fact, the physics and how efficient accretion of mass is by a compact object during such a spiral is a very exciting question. And there's a lot of research going on about that as well, whether you form an accretion disk, whether you eject a jet as a result of that accretion disk. Those are questions that we don't know the answers to yet very well, but they would most likely affect the morphology of this cloud of gas and how the spiral looks like. So that's very important too.
Great, thanks. I have another question from our team. There's been a lot of development recently in gravitational wave detectors, right? And there should be a few more instruments coming online in the future, right? What do you think would be the biggest steps forward that these instruments will provide?
Oh, that's a really exciting part. So especially in the mid-30s, a little more than 10 years from now, we are currently building two big instruments. One is going to be quite similar to the instruments we have now, Einstein telescope, for instance, or there is an American counterpart of that as well, possible, that would be able to detect similar sources to the ones we see now, but much further out as well. So we would really be able to scan throughout different redshifts, not only the sort of nearby universe that the current detectors are most sensitive to. And this is exciting because it allows you to probe evolution of the universe, evolution of galaxies, different sorts of galaxies, and all throughout the cosmic history. But that's just a small piece of that science case anyway. There's a lot that this detector would do for us. What is also exciting is the other big mission planned. That's a space mission, a LISA detector. In that case, that would be a few satellites floating in the space on the edges of a triangle. So I haven't talked about the interferometry and the detection technique of gravitational wave sources, but in that case, the mirrors of the interferometer would be much more far away from each other in the space than there are now in the current detectors. And the big thing about that is that we'll be sensitive to a different frequency range of gravitational wave sources, lower frequencies. So not just seeing stellar black holes like we detect right now, with LISA we'll be able to look into those supermassive black holes or intermediate massive black holes that you mentioned in the beginning as well, and probe a lot of the exciting science there. But again, I mean, that's a whole new topic for a whole different talk about the loud future of gravitational wave astronomy.
Yeah, it certainly is exciting. I had one more question. You said sort of understanding the formation channels, right, is an important next step. Can you get that information from the gravitational wave detection itself, or does that information really come from understanding the precursor things by using sort of multi-wavelength astronomy?
I think, yeah. So I think there's a lot that has to improve in our understanding of the channels, and how, because right now, you know, we can make theoretical predictions for what would be the signature of a particular formation channel on what we see in the waveform, what we see with the gravitational wave detector, on what are the properties of the source. But most of this detection, well, most of this characteristic, these predictions is still too uncertain to be used effectively to distinguish between channels. There are, however, few possible features that are most likely robust among the predictions. For instance, if we were to see an eccentric merger of black holes, so in the final in-spiral phase, we only see the very final bit of in-spiral. So in all of the binary black holes we've seen so far, at that point, there was no trace of eccentricity on the orbit, because by the time the two black holes get very close to each other, the orbit, any trace of previous eccentricity is lost. But if we were to see that in the data with the current detectors already, and eccentricity there, that would be an indication of a specific dynamical channel, and that would be very exciting. But I think there is a lot of work to be done on the side of, at least on the side of theory and modeling too, to really disentangle between channels.
Cool. Well, thanks, Jacob. That's really exciting. I do want to say, if there are any further questions, you can still leave them in the chat. I'm sure Jacob will be able to look there and answer. So yeah, thank you very much. We'll now move on to the next part, which is our quiz. So Stella is going to present our quiz.
So first of all, you can go to this tiny URL to find the Google Forms, like always. I also wanted to point out that it is possible to use the Google Forms on your phone if you want to see the slides on your computer and then the phone on the other side to answer the questions. So keeping that in mind, in case you want to use your phone and actually type out the link, I will give you a little bit of time to do that in this place. I will already start introducing the first game. Hopefully you guys are catching up, but I will go slow. So the first game, as it said here, is transient spotting. And I have an example case here. So what we want you to do is compare the two images that we show you, and to tell us whether you spot a transient on that image or not. And what I mean by that is, for example, on this first image, there is nothing happening here. But now on the second image, we see that there's suddenly as if a new star here. This is obviously not a star, it's actually a supernova event that is caught on this image. So we want you to go through these images and see whether you can spot other supernovae happening in our questions. Yeah, I think let's start slowly. So this is the first question. Do you see a transient here or not? All right, moving on. How about here? Is there transient or not? Moving on, number 3. Okay, moving on. Number 4. Number 5. I think this one is maybe a bit longer time. There's a lot going on here. All right, moving on. You can stare at it more later. Yeah, is there a transient here on the 6th image? And moving on. How about here? Moving on once more. Do you see a transient in this one? And the final question in this game, do you see a transient here? All right. So you can look at them again later, either through the going back in YouTube or just looking at them as they loop through while we're on a break. So the second game is called Binary Star Trivia, and I will then start it off. So this image shows an artist's rendition of a binary star system. How do the temperatures of these two stars compare? A, the red star is hotter. B, both stars have the same temperature? C, it is impossible to measure the temperature of stars. Or D, the blue star is hotter. Question 2. If one of the stars in a binary explodes in a supernova, what usually happens to the other star? A, the other star explodes too. B, the other star is flung out of its orbit. C, the other star immediately collides with the supernova remnant. Or D, we have no way of knowing. Question number 3. In roughly 5 billion years, the sun will reach the end of its life. At that point, which type of stellar remnant will be left in its base? A, a white dwarf. B, a neutron star. Or C, a black hole. Okay, number 4. What is the most common way binary systems form? A, two stars pass close enough and start orbiting each other. B, the collapsing envelope of gas and dust splits and forms 2 or more stars instead. Or C, a collapsing star spins so quickly that it splits in 2. All right, and question number 5. Which of the following is the closest double star system to Earth? A, Alpha Centauri. B, Chalisi 412. Or C, Sirius. Okay, moving on. Here I have very crudely marked the stars of the Big Dipper constellation. So which of the Big Dipper stars is actually a binary that is visible with the naked eye? Take your pick. All right, and finally we have a tiebreaker question. How many supernovae were detected in the year 2020?
Great. Thanks, Stella, for the games, featuring a special appearance by Stella's cat, if you heard that. Our next speaker, who is not a cat, is Nadia Blagorodnova. Nadia is a research fellow, again, at the university, at Radboud University in Nijmegen, and doing something a bit different to Jacob. Nadia works on observations of transients or things that go flash in the night sky. And in particular, she focuses on transients that are caused by the mergers of stars. So she works on trying to understand how stars evolve when they have a companion star. So she's going to be talking about the last dance of stars, and an apt title, since Nadia is really passionate about salsa dancing, and you can see her here dancing one of her salsa dances, and she has given salsa lessons, and she's also performed in different teams. So over to you, Nadia, to talk about the last stellar dance.
Welcome, everybody, and hello, good evening. So yeah, my name is Nadia Blagorodnova, which nearly sounds as Blagorodnova, which is actually the topic of my talk. That's how observers call stellar mergers. And yes, I study stellar couples, but I'm especially passionate for this, final dance that the stars do, one around each other, just they become one. So this is very exciting. And yeah, stellar mergers. So how, stellar couples, this sounds interesting, but we have our sun as a closest example of a star, right? So you may think, okay, well, it's a single star. So how common can be systems which are born together? So astronomers, we call them binary systems, right? Stars who live in binary. So how common these scenarios are, right? So we have a single star, but we are talking about mergers and gravitational waves and binaries. Look how common these are. Well, just to relate this to something that we are more comfortable with, if we're talking about couples, let's talk about human couples as well, right? So let's say something like our sun with the mass of our sun. So these stars, not that our sun had a companion which it divorced from, but right, the rate of stars like our sun, which actually have a companion, is about the rate of divorces in the United States by the age of 50, right? So about only 20% of stars like our sun do have a companion. On the contrary, stars which are more massive than the sun, let's say 10 times more massive than the sun or more massive, about 70% of them actually live in couples or in triples. And this is kind of the rate of, marriages in the United States by the age of 50 as well. So, among massive stars, marriages, let's say, predominate the divorces. So this is how common they are. But yeah, we want to know more, like, how do they live together, right? So we start with this couple, and each couple has its own space, which you can see like this kind of mesh space-time grid that we have here. So a star is a beautiful equilibrium system between gravity, which is kind of pushing the star inwards, and the fusion processes which happen in the nucleus of the star, which kind of repel this gravity. But something can happen as that, eventually the hydrogen in the core of the star will finish one day. It will last for a long time, but one day it will exhaust this hydrogen. So then the gravity will start winning, and it will start compressing the core, and likely this fusion will start happening sort of like more external layers. And then it will start pushing outwards this like loose, envelope of gas, which is surrounding the very compact core. So then the star will start expanding. And when it expands, the gas will flow in agreement to these L points. So they're called Lagrange points. And we can imagine them like as valleys and hills in like this space parameter mesh. So the L1 point would be the lowest one between the two stars. So when the more massive star starts to grow, it will spill mass through the L1. But when the space of the second star fills completely with the gas, the next point where the mass will spill from the system will be this L2, which is kind of behind the little star. So then what will happen? Well, imagine we have this binary, and we are seeing the binary kind of edge on. So every time the little star passes in front or behind the massive star, the larger star, we will have a dip in the brightness of the light of this star. So eventually we will have what we called eclipses. So this would be an eclipsing binary that we are seeing. So we can kind of perceive the variation of its light in kind of a sinusoidal fashion. But when one of these stars completely fills its space, and it fills its companion space, and it starts losing mass through this L2 point, what will happen is that this mass will start to be lost around the system, or will trail the system, And when the mass loss rate is kind of substantial, it will start to obscure the small component. So then we will start losing this kind of sinusoidal signature that we were seeing before. So then if we see this system from the top, what we would see is kind of a spiral of gas that was lost from the system. And this spiral also will kind of shock itself. So it will create these hot areas, which are marked in red, and it will have some cold areas, which are marked with this bluish dark color. So these are simulation, but well, the best of all is that they actually correspond to a real event that we observed a few years ago. So if we look at this big plot, what we see is the variation of brightness in time for a system which was a binary in our own galaxy, and then it merged. So if we see from 2001 until 2007, there is a cloud of points that seem to go up, but they're very messy. So if we try to make sense of those points by looking at the periodicity in change of this brightness, what we can see is that eventually that was an eclipsing binary. And we see this sinusoidal signature, which is changing. And if you pay close attention, you will see that actually one of the peaks is getting lower and lower in agreement to what we saw before. So actually this mass loss from the system is actually obscuring this little component, so the little star. But what is even more interesting is that if we calculate how long it takes for one round around each other, which we'll call the period of this binary, we see that this period decreases really, really fast. So during the years, we can see this very sharp decrease, meaning that the period gets shorter, but that means also that the binary spins faster and faster and faster around each other. So what happens when two components, like a stellar couple, spins really fast? So just imagine that you also have your stellar companion, and then you decide to go on a frenetic dance, right? So you start to spin, and faster and faster and faster. So what will happen if you have, like your long hair, it will start kind of flying away, your dress, your shirt. And if you have some like loosely bound objects, like hats on your head, they probably will fly away as well. So this is exactly what happens with a binary couple. All the gas, which is not really strongly attached to the system by gravity, will eventually kind of fly away when the binary starts spiraling faster and faster and faster around each other. So this is the video that Jakub already showed, but this shows that in this faster spinning, the binary will also approach each other in a way that it never did before. We see that the cores are approaching, and then we also can see how this gas is really expelled in the system in kind of spherical way here, right? But then I mentioned, wait, just before this happens, you just told me that the binary loses all the gas in its orbital plane. So what's going on? So, well, we have two components. We have this disk, which the binary created just before the merger. And basically the disk kind of stays with the binary, so it's bound to the binary. But then this mass, which is ejected during the merger, flies away. It may be a more or less spherical mass, but then it crashes with this disk, so it cannot expand kind of laterally, so it needs to be funneled through the poles. So basically in the poles, we find that the gas kind of flies away from the system, but this disk remains with the binary. So if we just zoom in a bit, how we would see this system? Well, unfortunately, we don't see, too much if we see the system very early on. But if we are lucky and we have HST, for example, we could see something like that. So this was another merger in our own galaxy. The merger itself is this red little dot in the middle. And what you see here is the reflection of the light of this merger burst on the clouds of gas that surround this binary or X binary. So this would be what we call a light echo. But yeah, here we don't really see anything, right? So what will happen if we look at one of these mergers a few years after the merger, right? When all this gas has cooled down to really uncomfortable temperatures of about like minus 260, minus 160 degrees, then we will need something, different to like an optical telescope. We need something like ALMA. And then we can detect like how this gas is shaped, because enough time has passed so we can actually see how this shape is forming, even if the object is far away from us. So in this case, we see it's not a sphere, but it's rather this hourglass structure, because this gas was ejected, but it's collided with the disk. So then it was funneled through the poles. So then it's not a spherical object. And what this shape reminds you of? Well, there is one of the most beautiful objects in astronomy are planetary nebula. And these objects are definitely not spherical. So there is a great variety of shapes, but we know that there is a predominance of these lobes or binary structures, which really remind us this geometry that I just described. So if we study the central components of planetary nebula, we see that in some cases, those are compact binaries. So it's a binary that managed to expel all of its envelope and tighten itself. And in some cases, it's a single star, meaning that star has fatally merged in a single star, and all these layers are just a reminder of its final dance. So here are my 3 messages to take home. Stars living in binaries are way more common than we may think. They are very common. So when they do this last dance around each other, they can lose a lot of mass. They can lose a substantial amount of mass that can really shape one of the most beautiful objects in astronomy, which are planetary nebula. Thank you very much.
Great. Thanks very much, Nadia, for that exciting talk. It's really amazing seeing these nebula that are so beautiful. I wanted to ask you actually about, I suppose it's just my favorite object, Eta Carina, right, is one of these particular sources, right?
Right. So there are many, many theories about what Eta Carina is. Initially, the eruptions of Eta Carina were supposed to be like what we know like as a luminous blue variable, which is just like a massive star that farts a lot, right? So it just ejects like a massive burst of gas into space. But then it was really hard to explain these 2 lobes of Eta Carina. So then, there have been like many theories that it was before a binary that merged, but even newer theories suggest that was actually a triple system where 2 components merged. And then there is still another companion, which is still orbiting Eta Carina, which is also causing like kind of periodic bursts, of gas to fly into space every time it passes close to it. So yeah, it's a really fascinating object that deserves more careful study.
Yeah, it's one of the sources that even I know about, even though I don't work in this particular field. A question from our team also is, you didn't really say too much about the masses of the kind of objects, but say in our solar system, we've got Jupiter, which is sort of a failed star, right? Do you need something more massive than that? Or could an object the size of Jupiter, say, we've got exoplanets, lots of exoplanets of that mass, could they also cause such a final dance?
Right. I think it is possible, right? If something starts expanding, you will have like lower mass objects like falling and spiraling, but like the burst won't be like half or quarter as spectacular than if you have two stars.
Thanks. Just another question. Maybe you could explain why these planetary nebulae look so colorful.
Well, they look colorful because there's like a lot of gas at different temperatures involved and lots of different compositions. So most of the pictures are like fake colors, right? So some of the colors symbolize like the X-rays because, you know, you have in the center this very hot cores of these X stars or X star, which has like very high temperatures, which is heating the gas around it. But then you also have like gas which is farther away, which is like at much different temperature. So if you combine all that, then or if you also code the gas according to its chemical properties, you can also get really colorful pictures.
Cool. Thanks for that. I think there's no further questions just yet, but there are still a few more minutes. If there are any questions in the chat, perhaps you could answer them there. So thank you, Nadia.
Thank you.
We now go on to the answers to our quiz. So Stella.
All right. First, we have the transient spotting game answers. First there will be a huge yes or no on the screen, and we will also point out wherever the transient then was, so you can check with hopefully where you thought it was going to be, and then you can check whether you actually found the correct one. So here indeed there is a transient, and it's this big new light appearing on the side. Moving on. Here on the second one, there's also a supernova event that has happened, and you see this transient here. Number 3, there's no transient here. In fact, there's nothing new in these pictures. 4, yes, there is. And you can see there's nothing here and something here. 5, no, there's nothing going on here. This is just a Pleiades cluster in 2 different colors that we're showing you. 6, also nothing here. 7, yes, there is, and it is right here. The green is pretty bad to see in this white background, but hopefully you can see where the transient is. 8, there is indeed. It is this one here. And finally, 9, there is a transient, and it's a supernova event right here. Now the answers to the trivia game. So first one, indeed, the blue star is hotter. So this is the answer to this question, and I want to give a quick explanation. So here's the colors of the stars shown as compared to the temperature, the surface temperature in kelvins. So red stars actually have a cooler surface temperature compared to blue stars, which have a much higher surface temperature. And this there's the scale going from yellow to whitish and then towards blue. And this is related to black body radiation. So if one of the stars in a binary explodes in a supernova, what usually happens to the other star? The answer is that the other star is usually flung out of its orbit and it just starts going its own way. However, sometimes it can still carry on orbiting the remnant. So that's also a possible outcome of this event. 3. So the sun, the remnant of the sun will be a white dwarf star, which you also could have heard a spoiler of in one of the talks already. So it was a test of how well you listened. 4. The most common way that binary systems form is B. The collapsing envelope of gas and dust splits and forms 2 or more stars instead of forming just one. So it is also possible to have capturing events, but you actually need more than 2 for such events. So 2 stars passing close enough to each other to start orbiting each other is not going to cut it. Number 5. So the closest double star system to Earth is actually Sirius, although Alpha Centauri is closer to us than Sirius, it is actually a triple star system, not just a double system. So that's why the answer is Sirius in this case. And 6, which of the Big Dipper stars is actually a binary star that is visible to the naked eye? It is number 2, and you can see, you can next time, if you haven't seen it before, look up in the sky and check whether you can see the second star. So the 2 stars are called Alcor and Mizar. I hope I'm pronouncing them right. And in fact, it turns out that recently we have also found that one of them is itself a binary system, where the other one is a 4-star system. So together they actually make a 6-star system. So it's not even a binary like how we visually see, but more than that. But obviously the other elements of this cluster aren't seen. Just you can visually just determine the 2 separately. And finally, the tiebreaker: how many supernovae were detected in the year 2020? And the answer is over 17,000. So a lot. And today we only have one winner because we didn't actually have any astronomers playing. And the winner is Perseverance with 13 points out of 15. So congratulations, very well played. Actually, everybody played really well. And we will contact you through your email address that you left us, and to organize how you can get your prize for this win. So thank you, everybody, and I will give you back to Wendy.
Great, thanks very much, Stella. I like the name of the winning team or winning player. So if you enjoyed this tonight, we will be back next month, but you can also check out astronomyontap.org for other Astronomy on Tap events, many of which are streaming online at the moment still. But we will be back online next month on the 29th of March with another two talks, one about planet hunting, the other about astroseismology or oscillations and other stars. And this will be on the 29th of March. The good news is that this is the day after we go back to summertime. So looking forward to that. So a big thank you to both Nadia and Jakub for their talks tonight. Very interesting. We'd usually give you a beer glass after your talk, but we'll make sure that you get these. And also, as always, a big thank you to our team. It's a lot of hard work to put these events on, and yeah, we appreciate all of you. Anyway, have a good evening, everybody, and good night.